I'm very excited to invite George from MystenLabs, the co-founder and chief scientist who co-founded SUI Network, to talk about their new consensus algorithm, Mysticeti, right? That's the pronunciation. Amazing. So yeah, thank you, George.
Thank you for the invitation. It's a pleasure being here. It's the first time, actually, I'm talking about Mysticeti in public, and I'm glad the audience is more technical than other audiences, so I can actually really go into a little bit more of the detail, even though we don't have time for the full details. This works? Okay, so I am indeed George Danezis. I'm a co-founder of MystenLabs. Before that, I was with DM. I'm still a professor at UCL here in London as well. And today, we're going to talk about one specific aspect of blockchains, right? So there are many ingredients you need in order to build a blockchain, and to some extent, many of us who have built kind of blockchains have kind of looked at many of them. You need some way of sequencing transactions in common, or in general, more generally, try to make sure that there are no inconsistent transactions. Then you need some kind of way of executing either that sequence of transactions or the set of consistent transactions. Then you usually need some crypto magic to do a bunch of things, either to verify things, to prove things, or to hide things, depending if your blockchain also does some privacy or not. And then you need to sprinkle on top of all of that some tokenomics in order to make sure that you incentivize good things and disincentivize bad things, broadly speaking, right? And if you have all of these ingredients, you usually make a new blockchain, right, depending on how new they are. Today, we're just going to deal with sequencing, right? I'm going to talk about Byzantine consensus. And first, let me give a very brief and an opinionated history of Byzantine consensus, right? Because it is one of these primitives that is very old, actually, much older than many in the room maybe, and not quite as old as me, but nearly. And it has seen really a resurgence in the last few years. Like many other kind of cryptographic techniques that people thought were of theoretical interest, now actually we're engineering with them, which is fantastic. So in 1985, basically, a bunch of people from the theory side proved that consensus is impossible. Okay, this is a good starting point for any kind of inquiry, and this is not just about Byzantine consensus. Byzantine being in the context of some parties actively misbehaving. They actually prove it's impossible even if some parties crash. In fact, even if one party crashes in a big group of people, these people cannot agree on a common value. Now, this is not a very helpful result, of course, because from our intuition, we tend to be able to agree on something. So indeed, there were relaxations on that model that were possible in order to make consensus broadly possible as we understand it, right? And I think that the most significant result and the kind of pinnacle of the early work on consensus, in my view at least, and as I said, it's my talk, so it's opinionated, is practical Byzantine fault tolerance by Liskov and Castro in 1999. This is a seminal protocol because if you look at it, the latency is great. All the great ideas are already there. It's using modern cryptography, at least digital signatures in some of the versions, right? And they show that you can actually do Byzantine fault-tolerant consensus. You can tolerate a third of parties being actively malicious. Safety is unconditional, right? And in the asynchrony model, conditional on cryptography working, of course. And in order to get liveness, you just have to make some loose kind of like synchrony assumption, like eventually messages arrive within some time delay. That was fantastic. And then what happened is we enter what I call the Dark Ages, right? The Dark Ages is just this loss of interest in the broader industrial and research community about this topic. That doesn't mean that there were not very interesting papers published in that time. There were. Actually, some very interesting results were published in that time. It's just that basically the mainstream community around both cryptography and, broadly speaking, computer security, network security, was just openly mocking, basically, that field as being of, largely theoretical interest. In fact, there is a login article that is called "The Saddest Moment," And it says, watching a presentation on Byzantine fault tolerance is similar to watching a foreign film from a depressing nation. Okay? People were actually openly mocking people who cared about Byzantine consensus because they were like, look, we have these data centers, right? Everybody is trusting these big companies to process data in the data center. What's the problem, guys? Like, stop, thinking about, being paranoid and thinking about Byzantine parties. No one's Byzantine here, right, in the room. Like, what's your problem, right? And of course, that topic became again relevant when blockchains became prominent. Tendermint, I think, and the Cosmos ecosystem is the first large ecosystem that really put Byzantine consensus on the map as a way of doing blockchains. This is pretty cool, and we owe a lot to that ecosystem for that. And then Dalia Malki and collaborators created and designed Hot Stuff. And Hot Stuff was actually adopted as the consensus system in Libra DM as part of Facebook. I was part of that adventure, and it kind of became the kind of go-to protocol for people who want to build blockchains based on Byzantine consensus for a while after that. So that's pretty cool. Byzantine consensus is back in vogue. This is what we're doing. And in parallel with Hot Stuff, and actually as a result of us in Libra DM looking at Hot Stuff, we also started developing ideas of how to do consensus based on directed acyclic graphs, right? And in fact, it did came out of some of our frustrations working with Hot Stuff at the time as part of DM. So let's look a little bit at the kind of traditional, and I call traditional like the kind of Hot Stuff Tendermint-like consensus versus this DAG-based approach, right? Because we're going to spend some time looking at it. So in traditional consensus, there is a leader that plays a very active system role, as I call it, right? The leader collects transactions, determines a valid sequence of transactions to augment the sequence that already exists there, and then broadcasts these blocks around, maybe gather certificates, and helps the protocol progress from a systems perspective, right? They are a very active participant. Now, this is great. Hot Stuff shows that as a result, communication overall in the system is linear, so it scales in the number of validators. That's pretty cool. Has low latency. You can basically do it with few round trips. That's great. But the problem is that leader, because there are system participants, very often can act as a bottleneck, right? Everything goes through that leader. The leader has to use a lot of bandwidth to share with everybody else all the transactions and the proposals and all of that. And if that leader fails, things kind of stall, if you want, right? I mean, things wait until a new leader is elected, accepted, and then the protocol can resume, which is cool. So we're like, that's not really great, right? So we started thinking, okay, what kind of alternatives there are? And we started developing this line of work, Narwhal, Tusk, Bullshark. Largely my colleagues developed Bullshark at the time. That takes a slightly different approach, right? In DAG-based protocols, what happens is all validators that take care of the consensus kind of are acting symmetrically, and there is a leader that only basically plays a logical role to break symmetry, as I call it, right? Everybody produces blocks, everybody links to previous blocks and other people's blocks. Then basically the DAG of blocks contains transactions, and then what happens is that every so often you look at that structure, right? You use some logical notion of leaders in order to decide how to break symmetry, and that leads to basically a sequence, and we will see about that in a second. Now, what are the advantages of this approach, right? The advantages are that everything from a system perspective is symmetrical. All resources are used symmetrically. Networking, CPU, storage, everybody is using all of these resources symmetrically, and as a result, no one's acting as a bottleneck for each other, which is great, right? There is also a separation in a Narwhal-based protocol between sequencing transactions and actually performing the consensus, agreeing on the sequence, which means that if there are failures, even the leaders are not there to play that logical role for a while, throughput doesn't suffer. You keep basically agreeing on transactions, and then when a leader comes, you just commit a whole bunch of them without actually loss of throughput. You just basically increase latency, which is pretty cool. However, there is one downside to these families of protocols. They have higher latency. They have higher latency than the traditional Hot Stuff, PBFT even, like protocols. Like how much more latency, and what is the problem that creates more latency? Let's look at that for a second. So this is a graph from Bullshark. My colleagues are authors of that. It is basically a partially synchronous variant of a narwhal-based consensus. And we can see here this very lovely graph, which plots basically the throughput that can be achieved on the x-axis in thousands of transactions per second, and the latency on the other side of commits in seconds on the other side. And in orange, we have hot stuff for different numbers of nodes. And we can see that hot stuff, can basically achieve latencies of, a little bit higher than 1 second. Now, the throughput is much lower than DAG-based protocols. It peaks at 50,000, etc., for very low latency. But that's pretty cool. You can get a commit pretty much every second. That's nice. We would like that, right? On the other side, the kind of Tusk, which is the asynchronous version of Narwhal consensus, and Bullshark, which is the partially synchronous version, these things can really scale up in terms of throughput. You can really pump those transactions into like hundreds of thousands transactions per second and beyond, right? But look at the latency, right? Tusk, which is a fully asynchronous protocol, which is pretty cool that we can do this at all, right? For a while, we never thought these things would be practical, has a latency of 3 seconds. So you lose 2 seconds over hot stuff. And Bullshark, which is a great improvement, still has kind of around 2 seconds latency. That's not great. Now, you can do a few things to reduce, a little bit here and there, and great engineering progress has been made, but, those kind of gaps remain, if you want, right? I mean, you can improve all protocols and they kind of move up and down a little bit. So, can we have nice things, right? Can we get basically very high throughput and latency that is close to the latency of traditional kind of hot stuff like protocols? That's really the key question that we set to answer. Now, while we were working at DM was using hot stuff, and it's difficult if you work in a big company and they have like a system that is working to convince them to totally change their consensus, right? It's a sociological fact. We said, well, maybe we could just use narwhal-like dissemination of transactions to get really high throughput and use hot stuff on the other side for the agreement, right? And maybe we'll get the best of both worlds. Sadly, this is not quite the case we found at the time. This is, again, from the original Narwhal and Tusk paper. When we basically use Narwhal with hot stuff on top of it in order to do consensus, again, we're stuck at 1.5 seconds because Narwhal adds some latency to hot stuff. It is, again, 1 second to half a second more than just using kind of batched hot stuff, which is the baseline we evaluated against. Better than using Tusk at the time, so that was cool. But effectively, Bullshark has nullified that difference. Like doing Bullshark is the same as doing Narwhal with hot stuff. So that composition doesn't solve the latency problem. It doesn't bring latency down to the 1 second range we would like to have. Okay. So, what makes Narwhal-based consensus slower, to put it bluntly, right? And we have really identified 3 sources of latency, right? The one has to do with DAG certification. The other one has to do with how the leaders are structured across rounds. And the third one about the fact that there is a single leader. I'm reading it in a different order. And basically with Mysticeti, we are reimagining DAG-based protocols to try to eliminate these 3 bottlenecks. That's basically how to think about Mysticeti. So let's actually look at Narwhal and try to look at these 3 problems one by one. Now, on the Y direction, we have 4 nodes. On the X direction, we have the blocks they generate over time. This is how to read these graphs, even though they look like some religious ceremony every time. So what happens is in Narwhal, each validator produces a block. The block, let's say the yellow block, each of the blocks basically is certified, means that you share it with two-thirds other parties, they sign it, they give you back a certificate, you broadcast the certificate. That is what this little circle does. And then you basically broadcast it to all the other parties. And the blocks basically contain 2/3 links to back blocks from the previous round. That's the kind of like logic of narwhal. And then you perform that protocol round after round after round. This is just a narwhal structure. And the bull shark rule on top of that, which is simple, so I'll present that, is that every even round, you basically agree on a leader. This is like a predetermined schedule of a leader, right? Let's say the first round, 0, you pick the first node, then the second node, the red one, then the third one, the green one. So every even round has a leader that you have predetermined. And then what you're looking for is this shape that I have highlighted in red, right? If you see that the block of the leader, that big red block, is in fact contained on 2 subsequent, 1/3 plus 1, technically speaking, subsequent blocks that are certified in the next round, okay? Then you have a commit. So you know that this will never change. Everybody will eventually observe it. You can commit everything behind it, which are all the ones that I have basically behind. So agreeing on that red block commits all the nodes that have, the blocks that have 1 after that. And now the same applies, of course, to block 2. You can see that block 2 is actually contained in 2 blocks in the next round. And that, again, commits all the previous blocks that are connected from that block. These are the blocks that do 2. Anything that was committed before with 1 is already committed, so we don't recommit it. It's already in the sequence. OK? This is roughly how narwhal works. Now, first of all, notice that you might, the rounds are not just like sending a block, right? I mean, they involve having a block, certifying that block, sending and including the block in next, basically, blocks, right? So that's basically at least a round trip and a half of delay. That's one problem. Now, also notice, of course, that you might get unlucky. You might get really unlucky. Look, that node, that block in the first round there, just after the yellow one, it takes a while for that block to be committed. Right? In fact, that block there, the unlucky one, only gets committed here. Right? This is when I observe actually that I have 2 blocks that contain 2 that goes and commits all of that. Right? So the inter-block timing is longer because you have to certify things, and you might actually get very unlucky and have some transactions that are just not connected for a while to a commit. Okay? This is a problem, of course, because if you have a transaction there, you're like, why is my transaction waiting there? There have been commits on the way, but I just was not included. Okay, so one thing that we do in Mysticeti is we try to reduce the time between rounds. We're not going to certify anymore. We're going to remove these little circles, okay? Now, as I said, this big line of 2s, right, this big delay between that unlucky block and its commit, feels a little bit unnecessary, right? And it is, in fact, unnecessary. If you think about it, we picked the red block here as a leader that then gets committed. But honestly speaking, that top block here, that is the blue 2 there, also has a lot of support. It is also included in 2 subsequent rounds. Actually, it is also going to be seen by everybody eventually, right? So wouldn't it be nice if we could actually commit more things here that definitely will be seen by everybody who commits in the future, right? And we could. It's just that we don't do it, right? In traditional kind of bull shark. So what we're going to do in Mysticeti is to say, well, actually, we're not just going to have one leader every time we're trying to commit. We're going to commit multiple ones because actually we might get lucky and more things can actually be committed during a particular round. Okay? More things that are safe and that have support can be committed during a particular round. Finally, notice that, again, in bull shark, we have leaders every even round. But why is that, right? Let's take, for example, an odd round, this one, right? This particular block, again, is connected to 2 others, right? everybody is guaranteed eventually to see it and to agree that it is part of the DAG. There is no question about that. That's what these two links guarantee, if you think about it. But we're not actually using it to commit anything. We have to wait here and subsequently in order to actually commit it, right? Because we have picked to actually have leaders every 2 rounds. Wouldn't it be nice if we can actually make a decision to commit every round? And this way, maybe we will commit this sequence of 2s that otherwise would have been committed here already here. OK? And this is, again, what we're going to do in Mysticeti. We're going to commit every round, or try to commit every round, in order to, again, reduce the latency of unlucky transactions that are in these blocks. OK? So as I said, Mysticeti is the solution that just gathers all of these insights into just one protocol, right? And tries to apply these 3 learnings, if you want, into one consensus protocol and improve on narwhal-based protocols. Now, what I say is that consensus is a little bit like hummus. Many people try to make it, but the best one comes from Israel. Okay, in my experience. It's the same with consensus protocols. If you look at the sequence of consensus protocols that I talked about, one of the authors is usually Israeli for reasons that I don't entirely understand. So when we came up with Mysticeti, we're like, oh, wow, we came up with a good consensus protocol as far as we're concerned, and we don't actually have an Israeli co-author, right? It's a bit strange, or do we? I don't know. But then what we discovered, right? What we discovered is that actually Edith Kedar's group in Israel has actually discovered the core of the protocol already, right? So we actually did some parallel work there. So all is good. The best consensus protocols still come actually from Israel. So this is how Mysticeti works. And actually, this shape is in Edith's paper if you read it. So how Mysticeti works is, again, all the validators build blocks with transactions and backlinks every round, okay? But now they don't certify them, they just sign them. They sign them and send them on, right? So this block is signed, sent on. This block waits for a few blocks, 2f+1 blocks. It's signed, it's sent on, etc. Okay? That already reduces the latency between within a round. And then what we're going to do is we're going to pick many leaders, and we're going to commit every round. But here I'm going to show you just one commit, like how is one commit decided? And the commit needs to have basically this structure in order to be decided, okay, in Mysticeti. What we're going to say is, okay, I'm going to try to decide this block as a leader, okay? And we will see that we have many different leaders in a second, but let's just consider that one. What I'm going to look for in the DAG is, in the next round, I want to have 2f+1 nodes that vote for that block by including it into their blocks. So these are votes. And then in the next round, I want to have 2f+1, 2/3 basically of the blocks, certifying that block by linking to 2/3 of votes for that block. And if I see 2/3 votes and 2/3 certificates, I know that this is going to be in every sequence subsequently, and I consider that block committed. I also can make the negative statement, namely, if that block is missing, if it is not there, and I do see 2/3 of nodes not including it in their block, and then I see 2/3 of nodes including the votes that the block has not seen, I can also decide that the block will never be included. Okay? I can basically decide both that the block will be included or that the block will never be included. Okay? And these are the two good cases where I can actually move and make a decision. Now, this is easy. If you see that shape, either with the block present or the block absent, you can decide that the block is the next agreed-on leader and commit everything in its history. The bad case, of course, is if you don't see that shape. What happens then? Then you have to continue the protocol until something subsequent is decided, and then look back and try to commit or not commit basically that block. We are not going to go through that case because it's painful, and it doesn't give us as much insight as possible. Okay? So besides theoretically being an interesting protocol, that protocol also has advantages from a systems perspective. There is a single message, the block. It just is broadcast around, and really the delays are quite uniform in order to make it work in partial synchrony. So that's all good. And then what we do is we take that simple commit rule here, that simple shape, and we just say, well, instead of actually having a leader that we decide every 2 rounds, right? What we're going to have is multiple leaders potentially. So here in the first round I have 2 yellow leaders. In the second round I have two red leaders. In the third round I have 2 blue leaders and then 2 green leaders. So every round has multiple leaders, and we basically designate potential leaders in every single round. And as you can see, in the happy case that all the leaders are committed, basically we just commit basically as we go. Why is this blue? Oh yeah, it's blue because it's connected here. Good. It's good. The color coding is fine. Yeah? So as you can see, the delay in the happy case is much lower than having this very long kind of like potentially delay to commit. In fact, we show that this matches the kind of PBFT commit latency, which we believe, without kind of any optimistic tricks like everybody's honest and acting, is as good as it gets. We don't have a theorem about that. We would love to have a theorem that you cannot do better than this. Maybe you can, and that'd be exciting. Cool. So what does that all lead to? It leads to good things, right? As we said, here we have the same graph as we had before, right? Hot stuff is that red line that actually has outliers that are close to 1 second. It doesn't actually have very high throughput, sadly. It kind of saturates, even though it saturates at around 50K normally before the latency becomes too big. Narwhal and bull shark, as we have said before, can scale up the throughput, but are around 2 to 3 seconds. We actually have improved a little bit our implementations since then. This is narwhal with hot stuff here. And this is bull shark at 2 seconds as before. And Mysticeti, let's not take that line. That's a 10-node line. It's not particularly interesting for a blockchain. But the 50-node line is actually more interesting for a blockchain. As you can see, for even 100 transactions per second, these are half a kilobyte, we still maintain a latency under basically a second. For more reasonable loads of less than 50, we actually can have sub-second wide area network latency using these improvements. That's cool. That shows that you can really actually have sub-second latency and still scale up your throughput a la Narwhal. This is basically the result. Now, there are a few details here and there. We are actually planning on integrating this consensus protocol as the consensus protocol of SWI. SWI actually has a fast path that allows you to do transactions that don't need consensus quite fast, and then basically agree on a sequence to checkpoint, etc. It turns out this is great because you can have lower latency. This is not so great because now you have to actually certify each transaction individually. So in the paper, we actually show how to integrate that fast path into Mysticeti as well, in order not to have to do as much signature verification, which is a pain. We can also reduce a little bit the latency of the combined fast path and consensus. We can also do auto and lock in case, in some cases, basically the fast path locks objects, etc. So we kind of worked in order to integrate a fast path as well as a consensus path into that. Now, one additional thing that Narwhal does is it dissociates transaction dissemination from consensus. Namely, you send blocks of transactions and then you agree on them. We actually took that out. This separation of transaction dissemination and consensus added one more round trip of latency, and we have not seen yet a blockchain that needs that. right? Which means that, sadly, our blockchains are not widely enough used to need hundreds of thousands of transactions per second. And until then, we can actually serve the needs of a blockchain just by having one, basically, instance that basically inlines the transactions. So we did away with that. There are many strategies. We can reintroduce that in order to get higher throughput than hundreds of thousands of transactions per second when our systems take off. This is it. This is my conclusion. The conclusion is we can have DAG-based consensus with the symmetry and the system simplicity that they bring at sub-second wide area network latency. We can also integrate fast path into them if we feel this is still useful. And we can have high throughput, the kind of high throughput that these DAG-based protocols provide. And they use very little CPU power. They're not like very fancy cryptographically. They just use a ED 25519 signature. So you don't really notice that on your validator. You have a lot of space to actually do execution. We have a tech report out. Feel free to read it in its full glory. And thank you. Very happy to chat with you.
Thank you very much, George. If there are any questions from the audience?
Yeah. Up more than 50 nodes.
So we ran out of money. So, we ran out of budget, I should say. Doing these AWS experiments with more than 50 nodes, because you have to do lots of repetitions for each point as well, gets really expensive after a while. And, people are like, well, when we productize it, we will actually benchmark the production thing. I think for the research is fine because we're comparing also with the previous work that has 50. So that's basically the truth of it.
But there's no reason to think it will scale not in a good way.
So it will scale the same way as Narwhal does. There is a quadratic element to all these Narwhal DAG protocols in terms that all validators need to send their blocks to everybody else directly, right? So it's not going to scale to thousands, but it will scale the same as Narwhal.
For SUI with 150 validators.
Yeah, it will do hundreds, which is where we're thinking. Sub-second should be the case, yeah. Like the block metadata should not actually, really touch the latency too much, yeah.
Someone else wanted to?
Yeah, it was very similar because I noticed that the 10 node and the 50 node lines separate faster for Mysticeti than for the other two. So I was going to ask whether there was like a protocol reason why.
I think it is the quality of the implementation. So we have literally spent the last 5 years optimizing our hot stuff, Narwhal, Bullshark implementations, and we always compare to those. The Mysticeti implementation measurements were literally done, on the kind of new artifact. There is no reason for that kind of smooth way up, if you want. There should really be a very flat kind of like, on the latency graph that then shoots up at some point, because at some point the quadratic thing becomes dominant, right? That's the way to think about it, that while you're transferring data with some overhead, most of your overhead is transferring the data. At some point, you reach a scale where actually the transfer of data is not the overhead anymore. Your overhead is the overhead, not the bottleneck. Your overhead is the overhead, and that should shoot up at that point. So there is no reason for that gradual degradation. Yeah.
Great. Thank you so much, George. It was very interesting, and thank you for talking to us about Mysticeti.